Hello children, in this video we are going to talk about some important points that we have to remember when we are dealing with refraction problems, and we are going to manipulate some of the results we have formed which in the previous video. Okay, so the first important point that you have to remember here is whenever light travels from one medium to another medium, there is a change in speed. There is a change in speed of light. There is a change in speed of light. This is something that we have already discussed, right? Whenever light travels from one medium to another medium, there will be a change in speed. Now, what you have to remember here, whenever speed of light changes, the wavelength associated with that light also changes. That also you have to remember. Okay, there will be a change in speed. The second point you have to remember is due to the change in speed, there is change in wavelength of light. Wavelength of light. Okay, so let's represent this in the form of a diagram. Suppose this straight line represents the interface separating the two media. This is the first medium and this is the second medium. Okay, let n1 be the refractive index of the first medium, absolute refractive index of the first medium, and n2 is the absolute refractive index of the second medium. Now, corresponding to every medium, the light will be traveling with a particular velocity. Let's think that my first medium is air. First medium is air. Okay, so we know that the velocity of light is a constant. It will be moving with c velocity, which is equal to 3 into 10 raised to 8 meter per second. Second medium is some transparent medium, maybe water or glass, whatever you want to think, you can think. Okay, one transparent medium. Let the velocity of light in that particular medium be v. Okay, v. Now what we are going to do is we are going to write the relationship connecting refractive index and velocity and wavelength, something we have already discussed. That is, the refractive index, the absolute refractive index of the first medium is equal to the velocity of light in vacuum or air divided by the velocity of light in air. What is the velocity of light in air that is given here? That is c. Here it is given as c, so it will be c. So n1 will be equal to 1. So always remember, when you are dealing with air or vacuum, the refractive index will be marked as 1. Okay. Now, in the second medium, the refractive index n2 is equal to c divided by v. The velocity of light in vacuum divided by the velocity of light in the given medium, c by v. We know those two results. Now, if I am going of relative refractive index n2 by n1, this will be equal to how much? n2 is c by v, n1 is 1. So this automatically reduces to what? c by v. So if the first medium is air, then n21 automatically reduces to what? c by v, which is the absolute refractive index. Absolute refractive index of the second medium. See, n21 represents the refractive index of the second medium with respect to first medium. But the c by v results tell me that this is the refractive index of the second medium. Okay, so whenever one of the medium or the first medium is air, then the relative refractive index, that is n21, automatically reduces to 1. What? The refractive index of the second medium. Okay, refractive index of the second medium. Please remember this particular point. This point we are going to see whenever the first medium is air, we are going to write the result like this only. N is equal to C by V. N is equal to C by V. Okay, N is equal to C by V. Now, in the last video we have explained C is equal to nu into lambda. C is equal to nu into lambda. And what about V, velocity of light in medium? This is also written as nu into lambda. But you have to make a slight change here. I told you that velocity of light is different in different media. So in air it is C, that is C value is equal to 3 into 10 raised to 8 meter per second. Okay, so corresponding to this velocity 3 into 10 raised to 8 meter per second, there is a particular value for lambda. I am calling it as lambda itself, or lambda C I will call the velocity of light in vacuum. Okay, frequency I will write it as nu itself. Now when light enters the second medium in which the velocity of light is V, due to change in velocity there will be a change in wavelength. So here I will write it as the velocity of light in medium, wavelength of light in medium. So whenever velocity changes, my wavelength is going to change. Okay, but what about frequency here? This is a very important point you have to remember. When in refraction of light from one medium to another medium, due to change in speed of light, wavelength of light will change, but the frequency remains unchanged. Frequency remains unchanged. So here, what is the third point I should add? The third point I should add is frequency remains unchanged. I have asked this question several times. Which are the two quantities that is going to change when light travels from one medium to another medium? Velocity and wavelength will change, but frequency will not change. Frequency is same. Since frequency is same, I have used the same representation, nu for frequency, in both the equation 1 and in equation 2. Now let's take the ratio here. What will be the ratio? C by V is the ratio. Then what will I get? Nu into lambda C divided by nu into lambda M. Nu into lambda M. Nu and nu will get cancelled. So what will be left over? I will get C by V is equal to lambda C divided by lambda M. And what is the C by V? C by V is nothing but the refractive index of the given medium. Refractive index of the given medium. It is written here. C by V is the refractive index of the second medium. Second medium here. When we consider the first medium as air. So N is equal to lambda C divided by lambda M. So I am comparing this result. LHS of equation 3 with equation A. Okay. So I am able to write C by V as N. So I can write N is equal to lambda C divided by lambda M. So I am getting a new result here. Refractive index is equal to the wavelength of light in vacuum divided by wavelength of light in given medium. So here what I am getting is refractive index depends on wavelength. Refractive index depends on wavelength. So we are getting large number of results when we write down the relationship between refractive index and velocity, refractive index and wavelength, and you should remember all those points. Okay, so refractive index is equal to wavelength of light in vacuum or air divided by wavelength of light in medium. This is another important result which we are going to use to solve the problems. So from here I am going to get some important concepts. That is, what are the factors affecting refractive index? Factors affecting refractive index. Factors affecting refractive index. Factors affecting refracting. The first point we have already discussed. It's the nature of the medium. Nature of the medium. When I say nature of the medium, it simply means the optical density. Optical density. Whenever optical density changes, the velocity of light in that medium changes. The velocity of light in that medium changes. From this expression, n is equal to c by v, the refractive index also changes. So I am getting an inverse relationship between velocity of the medium and the refractive index. If the velocity is greater, refractive index is less. If the velocity is more, refractive index will be less. If velocity is more, you call the medium as rarer medium. And according to this result, what am I getting? The velocity is more, refractive index has to be less, right? So refractive index is less. Refractive index is less. So for a rarer medium, refractive index will be less and velocity will be more. Now, what if the velocity is less? Then you call that kind of medium as denser medium. Now, if the velocity is less in this expression, if I say the velocity is less, so automatically the n has to be large. Why? Because n and v are inversely related. N and v are inversely related. Got it? So n and v are inversely related. So if v is less, I can write refractive index is more. So if I am seeing a greater value of refractive index, it means it is a denser medium. If I see a less value of refractive index, I will call it as a rarer medium. Now, till before this video, you were able to identify which medium is rarer or which medium is denser on the basis of velocity. Now, from this day onwards, you will be able to identify which medium is rarer and which medium is denser based on the refractive index concept. Okay, refractive index concept. So, refractive index less means rarer medium, refractive index is more means denser medium. So, the refractive index depends on the type of medium you are dealing with. This is the first factor that is affecting the refractive index. What is the second factor that is affecting the refractive index? That is physical condition. Physical condition. When I say physical condition, I basically mean temperature. Okay, with increase in temperature, the speed of light in medium increases. When temperature increases, I am symbolically representing, when temperature increases, the speed of light in the medium increases. So what happens to the refractive index? My refractive index decreases. Okay, what happens when temperature decreases? Velocity decreases. What happens to the refractive index? Refractive index increases. So when you are asked to write down the temperature dependence on refractive index, this is what you have to write. Don't write it in the symbolic kind of representation. You have to explain it. When temperature increases, the velocity of light in the medium increases and refractive index decreases. So what kind of proportionality I can observe between temperature and refractive index? Temperature and refractive index are inversely related. They are inversely related. So temperature increases, refractive index decreases. Temperature decreases, refractive index increases. Now what is the third point? The last point that I am going to explain here is the color of light. The color or I will say wavelength. I will explain this. Wavelength of light. See, corresponding to every color that you observe in nature, corresponding to every color, there is a particular value of wavelength. For example, The red color you see is having a particular value of wavelength. That is why you see it as red color. The orange color you see has got a particular wavelength. The blue color has got a particular wavelength. That is why you are able to see the blue color as blue, orange color as orange, and yellow color as yellow. So corresponding to every color there is a wavelength. So whenever color changes, the wavelength is going to change. And we know that how wavelength and refractive index are dependent. We already wrote that expression in the previous case. Refractive index is equal to the wavelength of light in vacuum or air divided by the wavelength of light in the given medium. So refractive index depends on the wavelength of light in a given medium. Okay, so remember those 3 points: factors affecting refractive index, that is nature of the medium, that simply means the optical density. The second point, the physical conditions such as temperature. The third point, the color or wavelength of light. This much point you have to remember. So if you want to solve the numerical problems, you have to remember all those expressions. Okay, you have to remember this factors affecting refractive index. I have extended the mathematical analysis so that you can understand these concepts. Okay, you will see a very little amount of equations in your textbook, but I have seen certain numerical problems in old CBSE question papers which is based on all those results. So you have to copy all those results in your lecture note. Okay, I will be giving all the equations that is in your textbook. In my original note, only that much will be present. But if you look at my lecture note, whatever things I am giving you as in this video, those equations will help you to solve the tricky kind of questions. Hope you understood this particular session. If you have any doubt, you can